Perfect. All right. So with that, I give you the floor. So next up is Mikhail Katz, who will be talking about effective infinitesimals in A. Please, Mikhail, the floor is all yours.
Thank you very much. A great honor for me to speak in Brisbane, first time in Australia. So let's see. This talk is based on joint work with Karl Hrbacek. So the corresponding paper with the same title as the title of the talk was just published in the journal Real Analysis Exchange. So it's online and you can access it via my webpage, via my homepage also. So this is an introduction to our work with Karl. Let's go over some standard notation. ZF will denote Zermelo-Fraenkel set theory. ZFC is Zermelo-Fraenkel theory, including the axiom of choice, the full axiom of choice as usual. And ACC is the axiom of countable choice, and ADC is the axiom of dependent choice, the weaker forms of the axiom of choice. So the claim is the following: these three theories that are listed here, ZF as well as ZF with the addition of the axiom of countable choice, and VF with the addition of dependent choice, are effective. So the question is, what's effective? What does effective mean? So this, of course, depends on who you ask. If you speak to a constructive mathematician, effective would mean mathematics that does not depend on the law of excluded middle. If you speak to people working in reverse mathematics, effective would be working in 5 systems of reverse of second order arithmetic. Okay, but for our purposes, I think what many mathematicians consider to be effective are arguments that do not entail set theoretic paradoxes and do not prove the existence of non-principal alter filters. In other words, axiomatic systems that do not prove the existence of non-principal alter filters would be considered effective. I think many classically trained mathematicians accept axiom of countable choice as well as axiom of dependent choice. In any case, many very, very basic classical results depend on those axioms. And you're still in an axiomatic system that does not entail set theoretic paradoxes such as the Banach-Tarski. So anyway, that will be our sense of being effective. And to acknowledge earlier work, I should mention that some of our work on the possibility of effective decimals exploits techniques developed earlier by Mitchell Spector, Eli Enayat, and Sam Sanders. So the theories that I will discuss are we chose to denote them Spot and Scott. These are initials of these are acronyms for the axioms of these two theories, and these provide frameworks for infinitesimal analysis in geometry, which are effective in the sense mentioned in the previous slide. More specifically, Spot is conservative over ZF, and Scott, a slightly stronger system, is conservative over ZF plus dependent choice. So here, this is an international conference. Not everybody is necessarily an expert. So I just want to ask the following question. What does conservative mean? Not all classically trained mathematicians know what conservative is. So maybe I will just discuss for a minute its relation to equiconsistency. As we know, theories such as ZF and ZFC are equiconsistent, but of course ZFC is much more powerful than ZF. Being conservative is a much more stringent requirement. It means that the theories prove the same theory, the same theorems. So our theory Spot proves the same theorems as ZF, and our theory Scott proves the same theorems as ZF extended with the addition of the axiom of dependent choice. Okay, just a minute to describe what this term means. So what we propose to develop is effective development of analysis and geometry based on infinitesimals. And this, of course, goes contrary to somewhat widespread perception that infinitesimals are ineffective, and we will show that they are effective in the sense that I explained. And for example, in our joint paper in Annals of Pure and Applied Math, we gave a proof of the Peano existence theorem for first order ODE effectively over ZF. And we gave an infinitesimal construction of the big measure via counting measures effectively, conservatively over ZF plus ADC over Scott. And so the plan for this talk will be to discuss compactness. First in the extension view, which is the better known perhaps approach to non-standard analysis. Then I will present the axioms of our theories, Spot and Scott, and then we will give our internal view of compactness, and discuss other further applications with regard to continuity, the Heine-Borel theorem, Peano existence theorem, and also we will mention that Nelson's radical elementary probability theory. It turns out it's a sub-theory of Scott, and in particular, it is conservative over ZF plus ADC, which, as far as I know, was not known. So let's start with the extension view, the more traditional view of the more traditional approach to the more standard approach to non-standard analysis. So here we extend the field of real numbers to the field of hyperreal numbers. And of course, there's a corresponding, okay, we'll discuss it in a second. So such, again, to emphasize, we're now in the extension view. Such an extension cannot be constructed in ZF plus ADC. Axiom of dependent choice is not sufficient to construct the hyperreals, and therefore such an approach cannot be described as effective. It's not our internal approach. In fact, in section 5, we will present an effective treatment of compactness. So let me introduce some notation. For any set NR, or the power set of R, or any set X, we will denote the corresponding non-standard extensions by the asterisk on the left side, star X. In some books, they denoted by X star. So such extensions satisfy the transfer principle. And there are a few ways of constructing them. They can be constructed either via the compactness theorem or via Alter powers in terms of a fixed non-principal Alter filter, which is not available in our internal frameworks, as I mentioned. And so let me just give an elementary proof of a lemma for a finite union of sets. The star of the union is the union of the stars. These are the star here. So this is just an illustration of applying transfer principle. If you have two subsets of a set X, then the membership in Y, membership in the A union B can be defined by this first order formula. And applying upward transfer to this formula, upward transfer amounts to attaching stars to all sets that occur in the formula. And this is exactly means that the star of the union is the union of the stars in the case of two sets. And the general claim follows by induction for a finite number of sets. So next result that I want to mention is this theorem. Suppose we have a nested decreasing sequence of non-empty subsets of R, let's say, indexed by the natural numbers. Then the sequence of a natural extension, star AN, again indexed by the standard N, has a common point. So I will not go into the proof. This is a kind of compactness result. I see there's some some of this is off the screen. Involves an application of the transfer principle. So more generally, if we define for a collection F, we say that it has a finite intersection property if any finite intersection of the sets is non-empty of families of sets in the family. So, as is well known, the theorem that I mentioned on the previous page is equivalent to countable saturation. That if you have any family of subsets that has a finite intersection property, then the intersection is not empty. Again, not intersection of the sets themselves, but the intersection of their stars, their non-standard extensions. Okay, good. That's called countable saturation. I want to mention it because it's used in some of the results that will appear later. So again, we would like to discuss compactness, first from the external point of view and then from the internal point of view. So let's recall some topological preliminaries. A topological space T is called second countable if its topology admits a countable basis. And T is called Lindelof. A space T is called Lindelof if for each open cover the countable subcover. So this is a more special property than second countable. Second countable implies Lindelof. And so, for example, if T is a separable metric space, which is basically the framework of classical analysis, separable metric spaces. Of course, not a functional analysis, classical analysis. Then T is second countable and has Lindelof. And here ACC is not needed for this assertion. And the framework of Lindelof space is sufficient for classical analysis, dealing with compactness and that kind of thing. So the theorem, assume that space T is Lindelof, then the following two conditions are equivalent. T is compact in the classical sense that every open cover admits a finite subcover. And the alternative characterization is that every element is near standard. Every element of T star is near standard in T. In other words, this element Y is infinitely close to a standard point of T. The advantage of such a characterization is, of course, is that it involves no quantification over sets. You don't need either open covers nor sets. It's a first order characterization of compactness. It involves quantification over points only. Okay, good. So this is a well-known advantage of the infinitesimal analysis. And as I mentioned already, analysis of infinitesimals does not require the axiom of choice any more than traditional non-infinitesimal analysis. As we see, some basic results in non-infinitesimal analysis also require mild forms of the axiom of choice. So far we discussed the model theoretic or the extension approach to non-standard analysis. Now we start discussing the axiomatic approach, or which is sometimes called the syntactic approach to non-standard analysis. The model theoretic approaches rely, as I mentioned, on strong forms of the axiom of choice. You need at least a non-principal alter filter. You need a little bit more, at least. Okay. The axiomatic approach can be more economical in the use of foundational material. So that's our philosophy. And it exploits a richer ST epsilon language. Epsilon here, of course, is the membership relation, the inclusion relation, \in. And ST is a one-place predicate. So what's that? What's this ST epsilon language? So let's try to explain that. So the classical foundational framework ZF starts with the empty set, then the empty set belongs to the set containing the epsilon set, and builds the semi-ring of natural numbers, so that using the axiom of infinity, then the ring of integers, the real numbers, That's all that is done in the epsilon language. A signature consists of a single relation, which is the membership relation. The internal or axiomatic set theories, of which the most famous ones are IST, Nelson's IST, internal set theory. They use the richer ST epsilon language, which I sometimes, for brevity, refer to as a stepsilon language. Stepsilon language is contrasted with the epsilon language, because I didn't put such terminology in any of our papers, but just for the purposes of the talk, we can call it the stepsilon language. So this language exploits the additional predicate ST in addition to the membership relation epsilon. ST is a one-place predicate standard, so that ST of X is read X is standard. Okay, so the theorem proved in the paper from 2 years ago in the Annals of Pure and Applied Math, Logic, is that the theory of spot is a conservative extension of ZF. We will see the axioms of spot in a second. And so in particular, it does not require any additional foundational commitments beyond ZF. And it requires neither the axiom of choice nor non-principal axiom ultrafilters. And these are not needed to do analysis with the infinitesimals. Now, I should mention here, probably it's appropriate to mention the following technical aspect. The separation axiom of ZF says that for any formula phi for phi from a suitable family, there exists a set such that an element belongs to a set if and only if phi of x, in other words, if x is true, phi of x is true. This, of course, remains valid in spot. Spot is an extension of ZF. But separation does not apply to formulas which involve the new predicate ST. And in particular, separation does not apply to the predicate ST itself. The collection of standard integers is not a set. And this is a feature that can be used, for example, to model the Sorites paradox. This was done by work by Portuguese mathematicians. I forget their name right now. I'm sorry. Okay, it skips my mind. So it's not a set. In other words, it's not a set that could be denoted by the usual set theoretic set builder notation. They could be described as classes, perhaps, or external collections. They can be viewed informally as classes defined by the corresponding predicate. And we use, sometimes when it's convenient, we use dashed curly brace notation to denote such classes. And so writing that K belongs to this curly brace notation is equivalent to say standard ST of K. In other words, K is standard. Okay, so that's the standardist predicate. Of course, this already was in Nelson's and Hrbacic's work from the 1970s. And so in many cases, the passage from a predicate to a set turns out to be unnecessary. For example, we don't need the set of infinitesimals to define the derivative. It's enough to work with a predicate ranging over infinitesimals. And for example, in Scotland can give a construction of the Lebesgue measure. Infinitesimal construction using counting measures over hyperfinite collections. So we call over non-standard finite collections. In BST, this is analogous to IST, but it possesses better mathematical properties. Lobe measure can be handled also, even though classically the lobe measures are developed by Lobe, they rely on the external sets. But in fact, this can be handled in BST, as Hrbacik and I showed in the paper that was published this year in Bulletin of Symbolic Logic. BST handles non-standard hulls as well. Some cases of non-standard hulls in BST were already handled by another Vakil in the 90s, starting in a series of papers starting in the 90s. So I want to mention, by the way, Guillermo, how much time do I have left?
So, in general, you have 30 minutes, and we start. Let me just double check, because since we are 12 minutes past the time, I guess that you have 12 more minutes or so.
Oh, okay, good, very good, very good. So I just want to make a few historical points. If I look at Leibniz, of course, didn't have set theory, he didn't have ultrafilters, he didn't have the axiom of choice, he didn't even accept the existence of infinite sets. He declared them to be contradictory. Nonetheless, one has to make a distinction here between procedures and ontology, procedures and set theoretic construction. So let's focus on Leibniz's procedures. So the claim is that Leibniz's procedures in infinitesimal calculus admit suitable proxies in modern infinitesimal analysis that are not available in Weierstrassian analysis. And let me give a few examples. Leibniz made a distinction between two types of numbers, assignable and inassignable. That's a distinction he spoke to several times in his work, in particular in 1676. And the predicate ST formalizes Leibniz's distinction. Inassignable corresponds to non-standard, and the natural number mu, which is inassignable, would correspond to Leibniz's inassignable numbers would correspond to non-standard natural numbers, and they would be greater than every assignable natural number. Another example, Leibniz had the heuristic principle that he referred to as the law of continuity. So this is was phrased as follows by Leibniz. Here, of course, we have Robinson's translation. The rules of the finite are found to succeed in the infinite, and vice versa. Robinson quoted this in his book his book Non-Standard Analysis on page 266. And the law of continuity, of course, is formalized by the transfer principle of Robinson's framework. Leibniz repeatedly emphasized that he worked not with the equality on the nose, but rather with the generalized relation of equality up to a negligible term. And this is formalized by relation of infinite proximity, defined in terms of standard part. Leibniz had an interesting concept. In Latin, this is infinitum terminatum. I don't know how to pronounce this. So this corresponds to a non-standard integer. Literally, infinitum terminatum means bounded infinity. And of course, this sounds like a contradiction in terms of the Weierstrass, in terms of the classical approach in the Weierstrassian framework. What's bounded infinity? Well, a non-standard integer is a bounded infinity, is a Leibnizian bounded infinity. Another example. So here we have a little table that gives a correspondence between the Leibnizian concepts and the concepts of non-standard analysis. I think I mentioned all of them already except for the last one. Leibniz specifically mentions in a paper from 1695, and in fact in a letter from the same year as well, that he makes it clear that infinitesimals violate Euclid Book 5 definition 4. What is that? This is better known to mathematicians as the Archimedean property. Infinitesimals violate the Archimedean property, of course. So I'll go through a couple of historical papers. One was published 2 years ago in the British Journal for the History of Math, and one was published this year in the Review of Symbolic Logic. Actually, it's online first. It hasn't been assigned to an issue yet, but it will be, according to my calculations, it will be assigned to issue number 4, the last issue for this year. And there are many papers on that at my homepage. You can find there. So let's another example. If mu is a non-standard integer, then its reciprocal 1 over mu is a positive infinitesimal, which by definition means that it's less than any positive standard real number. And therefore such an epsilon is necessarily a non-standard real number. a real number smaller in absolute value than some standard real number is called limited. Of course, in axiomatic non-standard analysis, it would be inappropriate to use the term infinite and infinite, so therefore we use the term limited, limited and unlimited instead of finite and infinite. So otherwise unlimited. So this is what in the model theoretic framework, this would be called infinite. We call it unlimited. And a basic fact, spot proves that every non-standard natural number is unlimited, and therefore greater than every standard natural number. So our theory spot, of which the axioms will come in the next slide, enables one to take the standard part, or what's called shadow, of every limited real number, denoted as h of r. And what this means is that the difference between r and its shadow is infinitesimal. That's what the standard, well, that's what the shadow means, or the standard part. And the classical definition, the historical definition of derivative would be the shadow of this differential ratio. So this is a more formal definition in terms of quantification over infinitesimals. And another example would be the Riemann integral, which is the shadow of this sum. It's a finite sum, but it's an unlimited sum. Again, because epsilon is infinitesimal, there is a non-standard number of terms in this sum. So either partitions into equal infinitesimal subintervals. And the relation of infinite proximity is defined by requiring that x minus y is infinitesimal. So okay, so let's get to see the axioms of spot. So it's a sub-theory of axiomatic theories that were already developed in the 70s, independently by Hrbacek and Nelson. Spot includes the axioms of ZF, and it also has 3 additional axioms: standard part, non-triviality, and transfer. The transfer asserts that if a formula is true for all standard inputs, then it's true for all inputs. This is, as I mentioned, the formalization of Leibniz's law of continuity. Non-triviality axiom asserts the existence of a non-standard natural number. SP standard part asserts that every limited real is infinitely close to a standard real. I should emphasize here that this is what this is somehow the punchline, because standard part is of course a consequence of the standardization principle, but the full standardization principle could not be included in effective theory because it would imply the existence of non-principal ultrafilters. So this is the punchline, that the standard part axiom, which is weaker than the full standardization principle, is actually enough to develop axiomatic analysis and classical analysis axiomatically. Equivalently, we can state it in terms of, without using the real numbers, in terms of subsets of the natural numbers. For every subset of n, there's a standard subset of n such that their standard members are the same. So this is, if you think of base 2 expansion of numbers, if you let a be a set of ranks where digit 1 appears, then you see how the standard part of a real number would be infinitely close to the real number itself. So this is just the equivalence of SP and SP prime. So that's what I summarize in this discussion here. So again, just to make things clear, let us compare the 2 approaches. At the beginning of my talk, I summarized the model theoretic approach. In model theoretic approach, you have 3 types of sets. You have the natural extensions of real sets, in other words, classical sets. You have the more general internal sets. And you have external sets. You have three types of sets in the model theoretic approaches. In axiomatic approaches, standard and non-standard sets correspond to natural extensions and internal sets of the classical approach. But there are no external sets. There's nothing corresponding to external sets. Unless there's a predicate, as I discussed in the context of the standard part of the standardness predicate. So that's the correspondence. There was internal sets in the classic in the axiomatic approach correspond in the classical approach correspond to all sets in the axiomatic approach. That's how things work here. Another important axiom, which is a consequence of axioms already listed. For me, this was a big surprise when Carl announced this. Idealization is actually, in this case, countable idealization, is a consequence of the axioms that are already listed on the previous page. So this is basically a leftward shift of the existence quantifier. You can take this existence quantifier and shift it over to the left of the formula. There exists an X such as for all standard n. So this was shown in our paper, level 2.2. This is analogous to saturation. So one of the reasons I wanted to discuss saturation is because it's involved in the proof of some of the theorems about compactness, but it's also analogous to saturation. It's also analogous to the idealization axiom. Another important axiom is SN. So this is standardization for Stepsilon formulas with no parameters. So this is also a kind of a case of standardization, that you can replace a set by but you can replace a Stepsilon formula by a standard set in such a way that all the standard elements of the set are exactly the elements that satisfy phi. And so this was for formulas with no parameters, but in fact, we show in our paper that you can also use parameters so long as they're standard. You can use standard parameters also. And this theory, another theorem what we prove is that this theory and Sn is conservative over ZF. The axiom Sn enables one to give an easy proof of the existence of the derivative function based on infinitesimal definition of the derivative. Okay, so Scott is a stronger theory that incorporates Sn and also the following choice type axiom CC. So this is if you have a formula with a Stepsilon formula with arbitrary parameters this time, then there exists a function that somehow the choice function for this formula. And the theory Scott has a slightly more intricate definition than Spot. So you have to take Spot and add these three axioms that I outlined. ADC is dependent choice, and SN and CC are the axioms that I just mentioned. And Scott also proves the following axiom SC, which is countable standardization, a stronger form of the types of standardization that we mentioned earlier. So this is for Stepsilon formulas with arbitrary parameters now. You also have standardization. Okay, so let me say a few words. I don't know how many seconds I have. Maybe I'm negative time already. Guillermo, how am I doing?
You can speak for 2 more minutes. That's fine. All good.
2 minutes. Okay, very good. So I promised to speak a little bit about compactness. We gave the traditional extension view of compactness with infinitesimals. Now we do it internally. So a point is near standard if again, there are no extensions here. Everything happens within the space itself. If for every point there is a standard point that's infinitely close to it. In other words, X is in the halo of the standard point P. And in the framework of Lindelof spaces, we could show that if every x is near standard, then T is compact. And this is, here you use countable idealization, which, as I mentioned, is an analog of saturation, which was used to prove the analogous result in the model theoretic framework. And conversely, if T is second countable, then if a space is compact, if the space is compact, then every point is near standard. In other words, this gives a non-standard characterization of compactness. And here you use countable standardization with a non-standard parameter. As we mentioned, it's available in Scott. And so we have the equivalence of two definitions of compactness for second countable spaces in Scott. Okay, so what we do in our paper, we also give effective proofs of equivalence of classical infinitesimal definition of continuity, of uniform continuity. And for example, the theorem of the continuous image of a compact set is compact. Other examples that we treat are the Heine-Borel theorem, and we give a proof in spot of Peano's existence theorem with the maximal domain of solution. This is a global Peano. And the proof that we give in our infinitesimal framework is actually more effective than traditional proofs found in books, classical ODE books by Hartman and Kurzweil, because they actually use at least countable choice. And we also prove Osgood's theorem on maximal solution, maximal in the sense of maximal value of solution. That's called Osgood's theorem. And this paper was just accepted for publication in the Journal of Logic and Analysis. And as I don't really have time to go into this, but the axioms of Nelson's radical elementary probability theory, they hold in Scott. Nelson's last axiom, axiom 5, is actually the axiom CC that I stated above. So therefore, Nelson's theory is a conservative over ZF plus ADC because Scott is. And all the results in Nelson's famous booklet automatically hold in Scott, including his S integral. Okay, so here is a kind of a question that's supposed to amuse the audience. One could ask, how could R contain infinitesimals? R is categorical. Okay, good. Some people find it puzzling to hear the claim that R could contain infinitesimals. So, and indeed, our perspective does not fit so well with the philosophy of the Platonist view of R. But it fits better with the relative view, such as that provided by the multiverse of Hampkins. And in fact, there is a close connection between the Gitman-Hampkins toy model of the multiverse and non-standard analysis, in the sense that two adjacent universes, the smaller one is the standard core of the larger one. So it's literally a model of BST, of a non-standard set theory, a pair of adjacent universes in Gitman-Hampkins toy model of the multiverse. So therefore, this constitutes a rebuttal of ad ultrafilter arguments. When people say that infinitesimals are not constructive because you need ultrafilters to use them. Thank you very much for your attention.
Thank you so much. Wonderful. So then maybe we go to a couple of questions.